All right, I promised we were going to talk about equilibrium constants, talk about the math a little bit. We're going to focus on setting problems up because I'm assuming that you can use a calculator and do math, so we'll give you one example of that, but we'll do most of the setups because that's what's new. Right? Equilibrium expressions. What we're talking about is somehow coming up with a generic equilibrium expression. So if I look at this particular equation, here is a real equation, and what I'm trying to do is get it into this form. Lowercase a, capital A. So the lowercase a would be the 2, all right? And this stuff over here would be A, which is my concentration. And then I've got 1B, and my O2 is my B. And then over here I have a 2 for the C, and over here I have SO3, which is the big C. And then I don't have any of this, so I'm just going to ignore that. All right, so calculating my equilibrium constant, what I do is I look at my SO2 and my square brackets here mean concentration. All right, and you'll notice that these over here are products. So it's always the concentration of the products divided by the concentration of the reactants. So notice my C and D are on the right-hand side. So my C is my substance, which is SO3. And so I'm looking at the concentration of SO3. How concentrated is this SO3 over here on the right? And notice that I have a 2 coefficient in front of it, and that's this little c. And notice that is going to be the superscript there. In other words, this is the concentration of SO3 squared. And it's going to be divided by the concentration of A. If I look at A is SO2. And it's also squared because it has a coefficient of 2 in front of it. Whereas my oxygen does not have a coefficient of 2 in front of it. It has a 1, and that's implied. So it's just the concentration of oxygen. So this is going to be my equilibrium constant. It's the concentration of sulfur trioxide squared divided by sulfur dioxide squared divided by the concentration of oxygen. Okay, so we're going to do a few of these so that you can see it all work out. Okay, now there are a couple rules we have to follow. The first thing is that it only works for gases and solutions. By the way, I'd write these down. I'd pause the video, write these down. The rules only work for gases and solutions. It does not work for liquids. It does not work for solids. So we just ignore solids and liquids in the equation. Did you get that? We ignore solids and liquids. We only do this for gases and things that are aqueous dissolved in solution. Right? And these square brackets, as I just said a moment ago, mean concentration. Now, the larger the equilibrium constant, the more complete the reaction goes to the right. So if we have an equilibrium constant that is really large, that's greater than 1, then more products are created. If it's really, really large, there are lots more products created. If it's less than 1, then there are more reactants. And if it's a really, really, really small number, then it's almost all reactants. And in fact, the closer this thing gets to 0, the more that we say the reaction just doesn't happen. Well, in reality, it does happen, but it happens a very, very, very little amount. So we say, well, maybe something isn't soluble, or maybe we just say a reaction doesn't happen. All right. But when you get up to equilibrium constants that are in the millions, or the billions, or the trillions, or the quadrillions, or whatever number comes after that, when you get up to those, then we say, well, there's so much more of the product that we just say it goes to completion. And then we don't think about the fact that it really is in equilibrium, that there's really still some of the reactants there. We just view it as it just went to completion. Okay. All right. So what we want to do is we want to write the equilibrium equation for this reaction. So again, the things we always do products over reactants. So we have products up on top, and we have reactants down at the bottom, and we're looking at these things are our coefficients here. All right. So we have the concentration of the product, which is HF, the concentration of HF, divided by the concentration of H times the concentration of F. Sorry, that's H2 and F2. Now let's look at our coefficients. The only coefficient that we have is the one over here on the product, which is HF, so that's going to be squared. So our equilibrium constant for this is going to be the concentration of hydrofluoric acid, or hydrogen fluoride gas actually, squared, divided by the concentration of hydrogen gas and fluorine gas. And since these are all gases, they all appear. Okay? Your turn. See if you can do this one. Pause the video. Write the equilibrium equation for this reaction. All right. Well, again, remember you're doing products over reactants. So the concentration of NH3 is a gas, so we're going to use it, and we're going to square it because of the coefficient in front of NH3. And then we're going to take the concentration of N2, and that's a reactant, so it goes on the bottom, and it does not have a coefficient, so it's only to the first power. And then we have the concentration of H3, which also is a gas, but it has a coefficient of 3, so we're going to cube it down here. So it's the concentration of H3 cubed. And that's going to give us our equilibrium constant. Okay? That's it. Now, if we had numbers for these, we'd just plug them in and do the math. All right. Go ahead and see if you can do this one. Be very careful. Hint, hint. Be very careful. So what'd you notice? Did you pick up on the fact that you've got two solids here? And remember, our rules say that we don't worry about the solids, so we just ignore them. So if we ignore this and we ignore this, what's left? Well, the only thing that's left is CO2. So our equilibrium constant is simply the concentration of CO2. And there's no coefficient to worry about, so that's your equilibrium constant. Very, very simple. Ooh, let's look at this one. This one's a little bit harder because you have to go and write the chemical equation. So be careful when you read this. Make sure you understand solids, liquids, and gases. Right? Go ahead and take a moment and write the equilibrium equation, and then see if you can come up with the equilibrium constant. All right, we have solid phosphorus pentachloride. That's 5. And it decomposes in, and it decomposes into liquid phosphorus trichloride, liquid, and chlorine gas. And if I look to make sure that my equation is balanced, I notice I have a phosphorus on each side and 5 chlorines on each side, so I'm good. I'm balanced. Now, I notice that my PCl5 is solid, so I ignore it. And I notice my PCl3 is liquid, so I ignore it. The only thing I worry about are gases and aqueous substances. So all I have left is this. So my equilibrium constant is extremely easy because it is just the concentration of Cl2, because that's the only one that's a gas. Okay? This one's a little bit more complicated, but the logic still remains the same if you think through it. Okay, so pause the video, go ahead and write the equation, and then write the equilibrium constant. All right, there are a lot of distractors in here, like the fact it's deep blue. I mean, I know that, and you've played with some of this in the lab, but anyway, copper 2 sulfate pentahydrate. Now, what does it tell you about this substance? It tells you that it's not only deep blue, but that it's a solid. So that's a solid. And it says it's heated to drive off water. So all you do is just apply some heat to this. By the way, we should have double arrows on these. You apply some heat to these, and you drive off the water vapor, which is H2O. Notice it says water vapor. H2O, good, Skip. And it's a gas. Now, how many water vapors do we have? Well, you'll notice you got 5 over here, so we have to have 5 over here. So it's water vapor plus leaving solid copper sulfate. And we are balanced. Now, what do you notice? Well, we've got a solid. We got a solid. The only gas we have is this one. So our equilibrium constant is simply the concentration of water to the 5th power. All right. At high temperatures, elemental bromine, this I think is our last one. At high temperatures, elemental bromine dissociates into individual bromine atoms. These are all gases, by the way, in case you didn't know that. Go ahead and see what you can do for an equilibrium constant. Well, the key here is it's at high temperatures, and that's how you know that they're both gases. So if I take bromine, which is a gas and it's diatomic, it says it decomposes into individual bromine atoms, which are still going to be a gas, but there are two of them. All right, so what's our equilibrium constant? Well, our equilibrium constant is going to be the concentration of Br, and because there are two of them, remember it's always the products over the reactants, divided by the concentration of Br2. All right, well, we have some numbers now. We're told that our concentration of Br2 is 0.97 molar. 0.97 molar. And our concentration of our gas is 0.034 molar. Well, I notice I have two sig figs in my problem, so I'm going to end up with 2 in my answer. And let's see if I can just plug some numbers into here. I get 0.034 on top, and I have to square that number, and I have to divide by 0.97, because that's our concentration on the bottom. All right, well, if I take 0.034 and I square it, and I divide by 0.97, I get 0.0012. Now, what are our units? There are no units. So for equilibrium constants, it's just a constant, it's just a number. There are no units that we write down for equilibrium constants. So there's an example of doing it mathematically with the once you've set up the equation. All right. One thing to remember, and we've said this before, but I'm going to say it again, catalysts speed up the reactions in both directions. So catalysts do not change the equilibrium constant. So if we added a catalyst to this reaction, if there were a catalyst for this reaction, it is not going to change how much bromine we get, bromine Br atoms, and it's not going to change how many Br molecules we have. Right, that's going to remain, that ratio, this number, your KEQ, is not going to change. Right, it's just going to happen faster, sooner, whatever. Okay, that's it, folks. I'll go ahead and do the worksheet. See you in class. Let me know if you have questions, or let us know if you have questions.